So tonight I'm going to talk about error handling with monads in Ruby. This talk is based on my blog post. You can find the link below. My name is Vitaly Pushkar. I'm a staff engineer at Solaris Bank. It's a bank as a platform startup here in Berlin. Let's talk about errors. What is an error? I like to think that there are generally two categories of errors that might happen during an execution of a program: expected and unexpected. Expected errors often come from the domain or the business logic of an application. For example, a user cannot be found in the database, or the sum of debits doesn't correspond to the sum of credits on an account, and so on. Also, it's errors caused by external application dependencies. For example, a network request in the absence of connection, an attempt to access a missing file, a request to a server that is down, and so on. So from the perspective of a program, these are not bugs. But if the program relies on having that user data or on the contents of that file, or server response, such errors can and almost certainly will become bugs if left unhandled. Unexpected, on the other hand, are errors that are hard or impossible to predict, but most importantly, such that are impossible to deal with. For example, a stack overflow or memory limits, hardware failures, and so on. Most unexpected errors are too hard or impossible to handle, while expected errors, on the other hand, have a long history with many different ways of handling. Today, I am focusing on the expected errors, and I would like to give a brief history of error handling first, to give you a better context for the main topic of this talk, which is the error handling with monads. So in the early years of high-level programming languages, such as COBOL, for example, go-to instructions were used for the control flow, including dealing with errors as one of the possible branches of program execution. Unfortunately, go-to is too powerful, and writing or reading any reasonably sized program would often become unreasonably hard. This frustration had led to the famous "Go-to Considered Harmful" paper by Edgar Dijkstra. He argued that this freedom to jump from anywhere to anywhere in a program provided by the go-to statement is leading to unreadable, unmaintainable code, and that it should be restricted to some standard structured control flow patterns instead. This paper sparked a debate in which the structured programming was born and suggested as a possible solution. Structured programming declares that any program can be implemented without go-to statements if a language it's written in allows just three basic things: if-else statements, sequence of procedures, and while loops. In structured programming, a procedure call behind the scenes is still a go-to. However, it's a kind of constrained and with less power. It can only jump so far to the beginning of procedures, for example. And roughly speaking, it is how procedures work even today in many programming languages. So despite being a beautiful high-level concept, procedures needed a way of dealing with errors that would be an alternative to go-to statements. So the first obvious solution to that were error values. With procedures as a concept that logically separates different computations, it's convenient to think of each procedure as a black box. These black boxes communicate by passing and returning values, and these boundaries between the black boxes are an excellent place for communicating about errors. Unfortunately, there are many problems with this approach, which I'll cover in my blog post. But for now, I should say that the most healthy approach is to return multiple values, one of which contains the result and another an error. It's explicit and leaves no ambiguity. It's the approach that is taken by the Golang Unfortunately, the need for if-else checks for the presence of the value or the error to learn if there was a success or failure makes this technique somehow cumbersome. And the same goes for the fact that returned values and errors can be of different, often not composable types, making it impossible to chain multiple such procedures safely. Then we have exceptions. Exceptions were introduced in the early versions of Lisp with the intention of fixing many of the problems with error values. The idea of exceptions is to free the code from the explicit error handling, make it more readable for the happy path. Another intended benefit was to allow better integration between libraries and applications by letting errors propagate from the library to the application all the way up. Over time, though, many problems with exceptions themselves were discovered, and some quite dangerous, making reliable error handling with exceptions not as simple as it hoped to be. Here are a few examples of such problems. Hidden control flow, for example. Well, exception handling flow, it lives in kind of its own realm, parallel to and hidden from the actual code. It's implicit and undeclared. Such nature of exceptions encourages programmers to simply forget about possible errors or even ignore them, leading to unreliable and possibly dangerous code. But even those who think about possible errors are left without any help. There is no way to tell a procedure that throws an exception from the one that doesn't. One would have to dive deep a rabbit hole to inspect the code of each underlying procedure, but even then, it wouldn't guarantee that some library hasn't forgotten to document an exception. Each line in any procedure potentially creates a possible exit point, which is impossible to tell from the procedure's signature nor from its name. It seems that the only way to write reliable code in the presence of exceptions is to wrap each line of code in try-catch blocks, but unfortunately, even that cannot save you from corrupting the state. One thing I only briefly mentioned so far is that when an exception happens and propagates up the stack, it unwinds the stack, so to say, and removes all the objects from the scope on its way up until it reaches a corresponding catch block. Such behavior intends to kind of undo or roll back everything leading to the error, to give the catching code a chance to try again. One problem with that is that without the context of what the lower level code was trying to do when the error occurred, the higher level code that caught the error cannot possibly know what caused this erroneous situation. And another problem is that the high level code knows nothing about the state that was changed by the lower level code before the error happened. And this state can be internal modifications to some global variables or some external things like database or service calls, file manipulations, and so on. So this unwinding cannot undo such changes, but that's not even the worst. Imagine if the code was modifying some big data structure when the exception occurred. So after the exception was caught, the data structure stays in a corrupt state. And such scenarios could and have already led to catastrophic failures. Another problem is the shifting semantics in Notion. Depending on the language, exceptions tend to have different meanings. In some languages, exceptions represent abnormal, unpredictable situations, while in others, they serve solely as a kind of control flow. And of course, there are languages where exceptions are something in between. But languages don't live in isolation. They live in ecosystems of communities like ours, libraries, books, online discussions, and so on, each influencing the style and the standards in which a language is used, including, of course, how exceptions are used too. And finally, concurrent and parallel programming are affected by exceptions too, because for simple multi-threaded applications, there is no best way to react to an exception in one of the threads. It's either unwinding up to the point of forking and deciding to keep other healthy threads, or killing all the threads. And each scenario can potentially to corrupt data. And when multiple threads don't simply fork join, but form more complex thread pools and communicate via some, I don't know, shared work queues and so on, each doing its little part, then there is nothing to unwind in case of an exception, because the original caller is detached from such threads and it's nowhere to be found to deal with the situation. And the same applies to the actor model, where actors can be not only local, but connected over the network. The fact that exception handling mechanism lives in a parallel realm, as I said before, and is not part of the program's control and data flow, makes it impossible to propagate exception between actors and across the network. With all its problems and simple scenarios where a discovered error can be turned into an error message straightforwardly, exceptions can be used to simplify the application code by only having exception handlers somewhere at the higher level of the application. In web applications, for example, it would be some middleware close to the web server or some high-level code that returns HTTP responses. It can also be used rather safely and easily in situations where expected errors are very few and the exceptions are caught immediately at the level where they are raised. In other situations where error discovery requires several, often non-trivial steps, with the context of the error and high degree of flexibility to handle the error, exception handling becomes significantly complicated, hard. It requires high discipline, attention, and it still doesn't guarantee reliable software in the end. But there is another solution, one that combines the explicitness and simplicity of error values and also eliminates most of the problems that exceptions try to solve. It's monads as return values. Monad is simply a container that wraps a value of any type and doesn't allow direct access to that value. Instead, it provides a uniform, structured way to change the value by running functions on it. Don't be afraid of monads. You don't need all the heavy math or category theory to make use of them, just as you don't need to know relational theory to use SQL or lambda calculus to write functions. There are many kinds of monads for various purposes, but in the context of this discussion, we are interested in one that is called either. The either monad represents values with two possible types, left or right, because most often the either monad is used to represent a value which is either correct or an error. By convention, the left type is reserved to hold an error value and the right is used to hold a correct value. But representing correctness is not the only use case for either monad, therefore such an abstract name. And in many languages and libraries where representing correctness with either is indeed the only use case, it's named more specifically. It's called result, with types failure and success instead of left and right accordingly. And this is the case for the Ruby gem used for code examples I will demonstrate in a couple of minutes. It's called dry monads, and it comes from the dry RB ecosystem. I encourage you to go to their website and check the documentation. There are a few rules that you should know about result before I show you the code example. Result can only be an instance of either success or failure. You cannot instantiate the result class itself. Result and its children, success and failure, implement the bind method. It's the method that executes any arbitrary code on the wrapped value by running a function on the value. And multiple such successes and failure objects can be composed by this bind method. If there is at least one failure in this chain of composed objects, it will be returned immediately, and the execution of the chain interrupts. Such composability removes the need for the verbose if-else checks, as in Golang example. So let's check some code examples. In the full version of this talk, I do a live coding with refactoring to refactor exception-based code to monad-based code, but considering time limits here, I'll just show you the end result. So what we have here is a super simple application just has users table, one user in that database, me, and the user object or the table has 2 rows, name and email. And the logic that this application has does one thing: it updates the user. So we can initialize the user updater class, and then we can call the call method on it with the fields to update. I will show you the call method body in a second, but what it basically does, it calls methods, validate fields, validate email, find user in the database, update user, and send email in a sequence. And each of these methods, it uses the result monad. So if the result of the method is successful, it wraps it in the success. If it's not successful, it wraps it in failure. And obviously the failure here, I'm using just a symbol, but it can be anything, right? It can be any object or anything that you need later. And it's similar for all the methods here. If it's successful, return success with the value inside. If it's a failure, return the failure with whatever you want inside. And you can also return just empty success if there is nothing if there is no value, if the method doesn't return anything but just has some side effects. So finally, the call method, and don't get afraid, don't get scared. For learning purposes, I think having this deep nesting is actually pretty cool because it shows you the logic. In real applications, I'll show you in a second, there is a synthetic sugar in this library to make it look nicer. So what happens here is whenever you call the validate fields method, and you remember it returns either success or failure, if that we then bind to the return to whatever the method returns. If the method returns success, then we continue and we get the value. In this case, it's fields, an array of fields. And then we keep binding. We keep calling our other methods, and we keep calling the bind and extracting the value from inside the success, and so on and so forth, until we end up with the result of this computation. However, if at any point any of the methods returns a failure, the whole chain is interrupted, and the failure is immediately returned to the caller. So as I promised you before, there is a synthetic sugar to make it look nicer, which is assigning intermediate values to local variables here. And then also there is an important thing to mention is the use of try. Try is just another kind of either. It wraps code that can cause exceptions. So in this case, it's a code from some SQL library, it can, or whatever, your database library, so it can raise an exception. We want to wrap it to catch the exception and transform the exception into the failure. But if it's not an exception, we just wrap it in success as usual, and it doesn't change how your application looks like. So basically, try is a special case of either, just as result is a special case of either. And finally, we can make it a little bit nicer by having some guard clauses here, returning failures immediately and returning successes later, and so on and so forth. And in the end, in your endpoint, it will look something like this. You instantiate the class with the dependencies, then you call the call method with parameters. In this case, it's ID and name or email. And then you need to do a extraction of the result, because right now it's a success or failure. And you need to check if it's a success, you can extract the success object and do whatever you want with it. If it's an error, extract the error. Well, this is a very simple version, right? In the real code, you would have much more such classes that can return successes or failures. You would combine them together. You might want to somehow combine all the failures together if you want to present them on a, I don't know, on a web form as all the errors combined, and so on and so forth. But generally, that's how it looks. And I would like to continue with discussing, so why all this hassle? Why would you want to use it? First of all, it's data. Unlike exceptions, our result and try monads are just objects, data. And data is the first-class citizen of the language. Data comes in, comes out. Data can be manipulated, can be transformed, combined with other data. It can be used to make decisions further in the code. It can be transferred, stored, and so on. Okay, it might not be the easiest thing to grasp from the first time, but so were exceptions when you learned about them. Yet, unlike exceptions, because error monads are data, it's right there in front of your eyes. It's not hiding from the reader somewhere a dozen method calls away. If there is a possibility of errors in the code you read, you see it in the form of result objects. It's concurrency friendly, so exceptions pop up to the point where a thread was spawned and blow up there without ever getting to the parent thread. Error monads are returned to the parent thread the same way as any other data, no additional work required. It also discourages forgetfulness and laziness. So let me admit it straight out. Because Ruby is a dynamic language, there is no way to enforce you to use result objects. But in my experience, when you are adding or modifying a method in a class where all other methods return result, you notice it and you remember about it. But also, if you call this bind method that I showed you on a method that doesn't return success or failure, it will fail, and that's remind about itself. But mechanics aside, the most important thing is that it encourages thinking about possible error scenarios. Writing code with error handling monads pulls you from this cozy, illusionary world of happy passes into reality. But what is the price of using monads for error handling? First of all, as I mentioned, it's not easy to grasp immediately. It's simple, but it's not easy. It requires the paradigm shift, especially if you ever been using exceptions or other styles for most of your career. It's not widespread. In every language community, there are its own sets of conventions and practices, and so on in the Ruby community as well. And although monads are just data, and there is technically nothing preventing you from writing your code with monads, because it's uncommon, you have to explain it and teach it to new colleagues every time and so on. And finally, it might be an overkill in simple applications. The flexibility either monads provide for handling errors in your code might in fact be not what you need. Now, for simple cases where turning an error into an error message for the user is straightforward, exceptions are still a valid solution, as I mentioned before. So in summary, if there is one thing I would like you to remember from this talk, it's the following. Don't be conservative. Try new things, give them a chance, but also stay pragmatic. When it comes to error handling, the path from error discovery to error reporting is what determines what degree of flexibility and control you may need. And I would like you to remember just this one thing. Today, you learned about one more tool to write safe, flexible, and error-free code. Go to the dry.rb, read the documentation, and give it a try. You will like it, I promise. Thank you.